Okay, so this is Newton's second law with friction. The last lab that we did was Newton's second law without friction. So what we're going to do is we're going to use a wooden block that will slide up the ramp. So there'll definitely be some friction involved. The first thing that you'll have to do, or I'll do, is weigh the block. Then for one of the runs, we'll have an extra mass for the block. So we'll effectively double the mass of the block. The mass of the block is around 200 grams. So we'll double that, and I'll add the extra mass when we make that run. So let's come over here to the ramp. So we'll have to set the ramp angles just like we did before. But in this case, what we're going to do is we're going to add enough hanging mass to the string. So this is M2. This is what we're calling M2. And we're adding the hanging mass such that you get a run that's about 2 seconds. Okay? So that's something that you have to kind of play with and play around with and then get a run that's roughly 2 seconds. I think that faster is a little bit better than slower, so maybe 1.5 to 2 seconds. And when I send you the data set, you'll see what I'm talking about. So we're going to do 6 different runs. We'll do a run, 3 runs at 25 degrees. At 25 degrees, we'll do 1 run with the block, large contact area. Then we'll have a run with the block on a small contact area. Then we'll double the mass. So I'll put the masses in there and we'll do a run. Obviously, for each of these runs, we may have to change that hanging mass. And certainly for the one with the extra 200 grams, we'll have to roughly double the hanging mass. You're doubling the mass of the cart, or you'll have to see how that goes. Okay, then we'll do a run at 35 degrees, which will be, the run at 35 degrees will be large contact area only, no extra mass. Then we'll do a run at 45 degrees. That will be large contact area, no extra mass. And 50 degrees, large contact area, no extra mass. Okay, so once you have all that data, then I'll go to the board and I'll show you what the calculations look like for this data set. All right, so I'm going to show you how to go through the calculations and calculate mu k. That's actually what we're after, the coefficient of kinetic friction. So we had a wooden block on a steel ramp. So that should be a particular value of mu k based on the wood and the steel. As we change the angle and change the contact area and the mass of the cart, mu k should have stayed the same within the limits of uncertainty. So we're going to do some uncertainty analysis and get a range for mu k. So we'll have a value for mu k, we'll have a value for delta mu k, which is the uncertainty in the coefficient of kinetic friction. So that's really what we're after, is calculating mu k for each run and the uncertainty in mu k. So I have up here just the standard setup like we had last time in the one we did without friction. I'm calling the mass of the cart big M, and the hanging mass is M2. Here's the free body diagram for the cart. You have the tension in the string going up the ramp. That's a big mg sine theta down the ramp. We had both of those last time without friction. But now we have this frictional force Fk down the ramp. That's opposite to the direction of motion. We had the block going up the ramp, so Fk is down the ramp. Then, of course, we have the acceleration due to gravity that is perpendicular to the ramp. That's mg cosine theta, and the normal force. Last time we didn't worry about the normal force and that acceleration perpendicular to the ramp because we assumed that it was frictionless. But now we need that to calculate mu k and Fk. For the hanging mass, it's just like always, just the tension and m2g. So like I talked about in the experimental setup, you're going to have a t value. I may send you just an average time that's going to be around 2 seconds. It'll probably be, a little bit less than 2 seconds, but somewhere right around 2 seconds. Make sure all of your data is in kilograms, meters, and seconds. I may send you the masses in grams. You need to convert that to kilograms. I may send you the distance in centimeters or some such thing like that. But we want to make sure that the forces come out in newtons for Fk that we're going to calculate, and a newton is a kilogram meter per second squared. So I've got the equations numbered. This is my suggested order that you would do the calculations. I mean, some students set up an Excel spreadsheet and do it very quickly, do it by hand. It's totally up to you. Just like last time, first equation, the acceleration is 2 times the distance over t squared, and that distance is equal to 0.8 meters. Delta A, I'm using the little small delta here for the uncertainty. Last time I used the triangular delta, but in the lab procedure, in this particular procedure, the notation is a small delta. So this is the uncertainty in the acceleration. It's A that you just calculated in 1, multiplied by 2 delta t over t, where delta t is equal to 1/10 of a second. That's the uncertainty in the acceleration based on the uncertainty in the timing. So this is propagation of error. We're going to do this through the entire calculation. Now we'll need Fk. Calculating Fk just comes from analyzing the free body diagrams, getting rid of t, and solving for Fk, which we've done in class and we'll do many more times. So Fk is equal to m2, that's the hanging mass, minus big M, that's the mass of the cart, times sine of theta, times g, minus m2 plus big M times the acceleration, which you calculated in 1, okay? This is the total mass of the system, m2 plus big M. Now we need an uncertainty in the kinetic friction term. So delta Fk is simply dependent on the uncertainty in the acceleration. Delta Fk is m2 plus big M times delta A. Equation 5, or number 5. So now we're in a position where we can calculate mu k. Mu k is equal to Fk, which you just calculated in number 3, divided by the normal force. Well, the normal force is equal to, from the analysis of the free body diagram, the normal force is equal to mg cosine theta. So now that you have mu k, you can calculate delta mu k. Delta mu k is the uncertainty in that coefficient of kinetic friction, and that's delta Fk, which you calculated down here in number 4. That's delta Fk divided by the normal force. One of the things that you'll calculate for this lab write-up is you'll do a plot of mu k with error bars based on delta mu k. So you'll have a value for mu k and then plus or minus delta mu k for the uncertainty. That gives you a range in mu k. For all of these runs, if it's a good experiment, a good lab trial, all those mu k should be very close to one another, and they should all agree within the limits of uncertainty, which is delta mu k.